Okay, good morning. Glad to be here and be part of this symposium. I think this is a very, I don't know. I think it's a very important topic. In fact, it's one that I think is, at least regionally, in fact, I think this is the greatest threat to the Great Plains in many different ways. Certainly was prior to this recent energy explosion, but it's at least one of the dominant threats to rangelands of the Great Plains. As Sherry mentioned, a chapter that Dave Engel wrote and I co-authored with him, we described it. We were trying to contrast the eastern red cedar, ash juniper, and other species expansions to the Dust Bowl. And we kept thinking, so the Dust Bowl is one of the greatest ecological disasters in the world and arguably in North America. I think this one sort of rivals it. It's different in some ways and similar in other ways. And one of the ways that it's different is it's very insidious. It's creeping, it's gradual, and that's what makes it somewhat of a problem, is that, you know, you just look up one day and basically you're in a different land. So it generally starts, if you think of the Great Plains, it's dominant in the south and east, spreading to the north and west. And I would argue that no one really knows how far it will go. And certainly with climate change, all bets are off. The implications of it are enormous. And so I'll use as a first example, and some of you may have seen me use this before, but this is the Sonora experiment station in the southern edge of the Edwards Plateau. And this is the stocking rate on the station that you can sort of translate into carrying capacity. It's a six-fold decline in a decade. And there's a lot going on in this. The way I typically describe it is we as the scientific community, I'm not quite that old, but we're focused on animal science, grazing management. We sort of had our head down. We measured everything you could measure about grass, tillering, production, how it responds to grazing, and then looked up one day and thought, dang, grasslands are gone, and it's mostly a woodland. And so Butch and Drac and others have been working to sort of try and reverse this change somewhat. But when you think about a six-fold decline in carrying capacity on this landscape, there's no grazing system's going to overcome that. Nothing you can do. You can't breed cattle better. This is the big deal. And I argue it's a transformation from 0 or 10% woody plants to greater than 50, which is about all that Sonora will support. You can move to Stillwater, 2 pastures, better than a decade. Pasture 2 eventually reached 0 in income from livestock. And pasture 1 is variable, but pretty consistent. And that's because it was burned all these years. So livestock production in that region in fact, I'll go so far as to say, without fire, you're out of business. If you don't like livestock and you like endangered species, there's the lesser prairie-chicken, and we can talk about that. Petitioned to be listed in 1995, likely to be listed within the next year. And its historical distribution through the southern Great Plains, a lot of people associate its decline to cropland. That's usually what's discussed. And cropland has been important. But if you look, the bottom part of that gold circle, which is the historic range, goes all the way down to the border of Mexico. And I don't know how many of you have been in that part of the country in the last 75 years. But basically, it is not open prairie. And in fact, the Sonora experiment station that I'll be talking about sits on the edge. There's data from the Kerr Wildlife Management Area of prairie chickens down that far. And prairie chickens are very intolerant of trees. In fact, so I argue over half of the prairie chicken range is now woodland, and that's really the dominant cause of this species decline. And in fact, it's not just opinion. We've done studies. Landscapes with declining populations had 15 times the increase in woody plants as landscapes with stable populations. So this is one of the primary causes, is a conversion from a grassland or shrubland to a woodland. If you don't like game birds, we can switch to songbirds. This is a study by Dave Engel and Rob Chapman, where grassland birds, which are the most rapidly declining birds in the world, we have their high dependence on woody plants. Some of them can't even tolerate 1 or 2 trees per acre. If you're more interested in nutrient cycling or other processes, and it shouldn't be a surprise, conversion from a grassland to a woodland, that everything's going to change. And water cycling, energy cycling, nutrient cycling all gets transformed. If you don't care about ecosystems and you're only interested in the human condition, just to continue to kick the dead horse, the human condition is dramatically impacted. This is Estelle Leviton's work from Tulsa, where she's monitoring pollen in the air and associating it to human or adult allergies and childhood asthma. And so we think about smoke causing air issues. We've got sort of this increasing insidious change in our air quality, and I happen to be allergic to it, which makes it really personally important. Okay, so my objectives today are not to only go through all the evil things about cedar, although that's part of it, but I really have 2 general things I want to talk about. First of all, I'm going to quickly, very quickly actually, review just general ecology about juniper. And it's interesting because in a previous century, I started a master's project under Fred Smeins, and he hired me to study understory, overstory relationships of ash juniper, and all my friends in West Texas said, "What's that? You know, what are you talking about?" I said, I'm studying what grows under cedar trees. And they said, "Well, nothing grows under cedar trees." And I said, "Yeah, but I'm going to prove it." And so that was the start of a wonderful research career. But there were a lot of studies, there have been a lot of studies done like that. Collectively, they are informative. But one of the things I noticed was when I went around to talk about this as a naive young researcher, I didn't have the answers to the questions that most people were interested in. They were mostly interested in how long does it take to form a woodland, how much fire is needed to keep a grassland open for a lifetime or more, those kinds of questions. And so I had the opportunity to develop a simulation model, and we're not going to get into the depths of it because it's not very interesting. But I'm going to present some results from it, and hopefully try and answer some of these broad questions. It basically is a situation where I can use these small-scale studies, develop a model where the change can occur, and then we can impose treatments on it that are like experiments and come up with results. So I'm going to focus on 2 sites in what I present. I'm going to call one low productivity, which is Sonora, the southern edge of the Great Plains. 20 inches of rainfall, which if you're from the west, that sounds like a lot, but it's on about 7 inches of soil. And you have a really long growing season. So it's actually a fairly arid situation. It's an oak juniper mixture, and we're mainly talking about ash juniper here. This is actually from the Kerr Wildlife Management Area, this picture, and this is somewhat what people describe as what it might have looked like historically. Although many of the historical counts, the trees were much lower, and if prairie chickens were there, they would have had to have been a lot lower. So we've basically seen this conversion from something like this to something like this, where you basically have very little understory, lots of juniper is primarily what you have. Second site, I will call high productivity, and those of you from Sonora or from Stillwater will be surprised that I'm calling Stillwater high productivity. But very similar in a lot of ways. It's an oak juniper savanna. It's different in some ways on the edge of the cross timbers, and generally limited by soils. It also differs in that it's eastern red cedar, which while it's a different species, those 2 species are very similar to each other in a lot of ways. They both die when they burn, essentially. And so this is outside of Stillwater. This is one of our original patch burn study sites, and in the middle of the picture there, you can see 160 acres that we patch burn with a 3-year fire return interval. In the background is a landscape that started out the same. And it has actually been burned a couple of times by wildfire and by prescribed fire, but it's not enough in the last 20 years to keep out eastern red cedar. When you get into the cross timbers, you have these small openings that are grassland. You kind of have this mosaic of grass and trees. Well, most of those openings have now filled in with eastern red cedar. Okay, so to review the field data and just give you an idea of what kind of information goes into this model, I'll just quickly go through and show some examples. And most of these show my age because they're not the most recent necessarily, but in truth, and I'm sure there's more that we could add. It's not intended to be exhaustive. First of all, we know how many seeds are produced by trees, and hopefully as I go through this, you'll see there's a logic. There's high variability, but generally high production of seeds. Trees vary, years vary. Seeds are dispersed by almost every animal out there, but most effectively by birds. So you have the production, then the dispersal, then you have germination rates, and under different conditions, many people think that grazing lowers the competition and you get an increase in trees, and that's absolutely not the case. I'll just say that. In fact, what we find is that grazing actually causes establishment to go down. So it's actually quite the opposite. And essentially, long-term grazing has minimal impact. We measured growth rates of juniper in a bunch of different ways at both sites. Then we have Nobel Prize winning overstory-understory relationships, or what grows under cedar trees, which is nothing. Although there are some exceptions, which is usually what researchers do, is find the irrelevant exceptions. Then we have a few long-term data sets, one of which compares grazing histories and looks at the rate of encroachment, and basically there's no difference unless the grazing happens to be goats. We have long-term data on the influence of grazing in the herbaceous community, have the influence of weather patterns on all of the above, and then finally we have the effects of fire on juniper mortality historically under fairly limited conditions, more recently under more extreme, which Drac will talk about. So all of these studies are important in their own right, but collectively you can actually start to answer some really big questions. So we were able to put this into a model where we have seeds dispersing into an open grassland. Those seeds grow up to be big trees, start producing seed. Then you end up with a forest. The cause of mortality that limits that is fire, which is dependent upon both frequency and intensity. And then in later years, we added a grazing model and eventually parameterized this for multiple sites where the grazing affects the herbaceous biomass, which translates into changes in fire intensity. And I'll just quick go through some of the output. This is kind of a challenge to look at first, but this is 150 years. So we can go back to 1870 and say, what if we would have done things differently? So in this case, what if we had not grazed it and had no fire? We're going to love it, basically. We're going to put our arms around it and care about it. Essentially, what to look at here is the red line. That sort of summarizes everything. It shows the potential herbaceous production you can have on this landscape, starting out at 100%. Sonora has a lot of rocky you're never going to get 100% trees, and you're never going to get zero herbaceous production. What happens there is we go from 100% potential production. The solid line is actual biomass, which is a function of grazing and weather. The dotted line are large trees. So we see after 60 years, we've basically lost herbaceous production down to about 30% of what it was historically. By 70, 80 years, so 1950, in the 1870 rule or starting point, we basically have a woodland. This is no grazing, but no fire. So what happens if we throw some fire in the mix for 150 years? In this case, we started out moderately grazed in this example, but we removed grazing, started just burning at a fairly infrequent interval, once every 10 years. But now this is starting with no cedar and starting at year 0. And with 10-year fire return interval, we can maintain grassland production at Sonora. Now, if we throw in grazing, this is moderately grazed, all of a sudden we start to lose the system. It takes a little bit longer. Here we have a 10-year fire return interval, and we see that by 80 years, we've had a significant loss of productivity. Now, this doesn't always happen with this model run. What's interesting is it becomes really sensitive to climate because we're right near a threshold where it can go either way in 150 years. So, just took these off of Google Earth. They're from the Sonora station. The top one is an ungrazed, unburned exclosure, and sort of shows the same thing we saw in the model. The bottom one is ungrazed in recent time, but burned quite frequently. There's actually a lot of data from the Sonora station that we can use to validate this, and the model actually works fairly well, and I'd be happy to share that with you. But the general point is when productivity is pretty low, at least relative to the Great Plains, even moderate grazing can have a big impact on how things turn out with fire. They can have a big impact on the way fire and grazing work together, and it can contribute indirectly through what I like to sort of call the fuel versus forage paradox. So what if we throw in Stillwater? Now here we have a little bit different format of a graph. We're basically looking at after 150 years. We've got treatments along the bottom that are different fire intervals. We're just looking at what was previously the red line, potential herbaceous production, and we're looking at Sonora, which is the low productivity site or the solid circles, and Stillwater, which is the high productivity site. And so you can go along the bottom with no fire, you end up with 35% production after 150 years, and those are mostly on little patches that don't end up with a lot of trees. Probably an underestimate at the reduction at Sonora or at Stillwater. When you put a 15-year fire interval, you can actually start to have an effect at Sonora at the low productivity site, but you have no effect at Stillwater. It really takes a 10-year fire return interval at both sites to start to limit the encroachment. And this is starting at year 0, so we're well past year 0. Now what I'm going to do is add moderate grazing to this, and what will happen is the solid line is going to change dramatically, and then the high productivity site, this is not going to change at all. So in this case, we're calling moderate grazing sort of the take half, leave half rule, and that sort of situation. So watch the solid line when you add moderate grazing. If you have no change in Stillwater, essentially it has no impact because you have more fuel. But it has a dramatic change. Now we're talking about a 5-year return interval at Sonora. And that's if you start burning at year 0, which was a long time ago. If you throw in hay grazing at Sonora, basically sell the farm, get some binoculars, start watching birds, because you're basically going to have birds that are attracted to cedar trees, which isn't all bad. It's an option. At Stillwater and in tallgrass prairie regions, you start to require a 2-year fire return interval, which just probably says something about why the Flint Hills are burned almost every year. They're grazed fairly intensively, and that's the kind of fire frequency it takes to keep junipers out. So to put these in sort of a summary graph, where you have ungrazed to the left all the way to heavy grazing to the right, and you can develop these two curves on how the two sites respond differently. So at Sonora, any mild increase in grazing intensity has a dramatic impact on the outcome. You require much more frequent fire return intervals. At Stillwater, you actually have minimal effect initially, and then it takes fairly heavy grazing to actually have a major impact on the relationship. So, like all models have assumptions, and the best thing to do if you're working on models is just to ignore those. But in reality, they actually tell you a lot more about the model than the actual data do. And so I'm going to go through a few assumptions that if we had not made those assumptions, I think the model would be completely different. And I've got examples in some cases. So first of all, the idea that we started this model with an open grassland, only juniper in the area that could disperse into the area, but not really any juniper on the site. You have to start somewhere. The problem is nowhere has that anymore, or almost nowhere. The majority of the world is not like that. And one of the things I did was I took the model that worked, which was moderate grazing with a 10-year fire return interval where you remove grazing the year before the fire. That consistently maintained an open grassland for 150 years. But instead of starting the burn on year 10, we skipped year 10 and went to year 20, and that really didn't have much impact. But when we skipped the first two, which would have gotten us to about 1900 in my example, the whole system comes apart and you basically have to remodel it in a whole different way. You would have to have much more frequent fire. So I guess what I'm saying is we should have started this a long time ago. And so as a result, this model, some of the results may be over less frequent fires than we actually may require. The other point is that I focused mostly on grazing with things that, as in the model, things that eat herbaceous biomass. And actually, as part of my master's, we also aged trees that had different levels of goat pressure. And you actually end up with trees that are twice as old per given age size when you have goats present as you do when you only have cats. So basically, a tree 6 foot tall would be a lot older. So you would have more time that would lengthen out the fire return intervals that could be possible. Another important assumption, a lot of my research recently has been on this patchy fire thing, and one of the things we've noticed is this really changes the fire grazing dynamic as you would expect. But when you imagine an homogenous landscape, a uniform, where grazing's uniform and fire's uniform, that's what creates this fuel forage paradox, where you either have to burn it or you have to eat it. And if you can create this patchwork where animals are grazing where you're not building up fuel, then you can actually overcome that paradox. And in fact, we've seen this on some of our study sites. Cedars that we were never able to kill before, we're killing because we've accumulated more fuel. Thanks, Sherry. Another important assumption I have to throw in, because Drac Twidwell's here and he's going to talk and he knows a lot about this, and he will make me look really bad because he's going to counter everything I say just about. And he's right. The cutting edge science I used originally in this model was probably from 1973, based on what we knew about fires and their effect on these systems. It's basically looking at using prescribed fires that everyone would feel pretty confident in conducting. In reality, when you get to these threshold conditions, there are ways to overcome this, and Drac's the one to talk to. The general idea, we typically think of the world as grasslands, kind of a typical state and transition model. As you move to the right, to the at-risk stage, you get some trees, so you go out and burn them, you go back to the grassland, and as long as you don't let the trees get too big or too abundant, you can limit their impacts on the fuel and you can still carry a fire. Well, what Drac and Butch Taylor and others have shown is that there's actually some other options, and one of them is this nuclear fire attempt, which is not only, it's crazy, first of all, but not only is it crazy, but it actually works. So Drac can talk about that. You know, we still don't know, obviously the picture on the left on the bottom is not a recovered grassland, so there's still some work at figuring out how to get that back, but we've sort of broken the threshold, at least initially. Okay, so to summarize quickly, ash juniper on the low productivity site, Sonora, without fire, you basically end up with a forest after about 60 years. Without grazing, even a 15-year fire return interval, if we had started in 1980s or 1880s or 70s, would have maintained a fairly open grassland. When we add moderate grazing, it takes a 5-year return interval. And heavy grazing, basically heavy grazing, you just can't do it for 150 years. And a lot of people have described that heavy grazing basically fireproofs the landscape. There's some exceptions to that, and Drac is a major exception, and he'll talk about that later. At Stillwater, Eastern Red Cedar, takes about 45 years. Again, if we were starting in 1870. Just about a 10-year fire return interval, we could have kept trees out. Moderate grazing really doesn't have much of an impact. Heavy grazing, you have to have quite a bit of fire, about as much as you can get on the landscape to keep trees out. So to conclude, one of the reasons we did this is people wanted to know, there's a lot of debate about what causes this conversion to woody plants. It's simultaneous to the introduction of livestock, there's climate change, there's a lot of things going on. Well, one of the things we were able to show is that if you model fire, you can actually get predictable results that are actually an indication of what actually happened. So fire alone can actually explain the patterns that we've observed. Grazing, studies show quite a few that basically this has very little direct impact, but it has a major impact, indirect effect, sort of on the fuel, fire, forage interaction about how much fuel do you have when you burn. There are thresholds everywhere, fire frequencies, fire intensities, timing of the first fire. We could come up with a long list of potential thresholds depending on how you want to define a threshold. Certainly nonlinear. The closer you get to the threshold, the more important interannual variability in rainfall is. So if you said, well, 15 years is the threshold for fire at Sonora, so I'm going to burn 15 years, all it takes is a few drought years to cause problems. And then finally, there's some alternatives: goats, heterogeneity, and extreme fire. And I don't know if I have no time for questions. It took too long to put these, no, it's okay. Thanks.